Welcome back. Today we're going to have a look at definite positive or negative definite matrices once more. And we'll have a look at an important criterion for positive or negative definiteness. And that is called Sylvester's determinant criterion. So that is a theorem. Sylvester's determinant criterion for definiteness. So remember, we're only talking about symmetric matrices if we want to characterize a matrix as positive or negative definite or indefinite. So this is also only formulated for symmetric matrices. So let's say we have a symmetric matrix. Let's call it A, and that's a matrix in Rn to the n. We call the entries of that matrix alpha ij, and then I and j will vary from 1 to n. For this matrix, we define submatrices that we call AK, and those are defined as the matrix alpha ij, where I and j vary from 1 to k instead of from 1 to n. So basically what we do is we start at the upper left corner and take a quadratic matrix that extends from that corner and is possibly less than the whole matrix. Okay, so this is a k by k matrix. And we define this for all k in 1 to n. So there's a1, a2, a3, and so on up to an. Okay, then we have the following two criteria. First, A is positive definite. If and only if all so-called leading principal minors of the matrix A are strictly positive. I'll explain in a minute what a leading principal minor is. If all leading principal minors, and this is just a complicated expression for saying we want the determinants of AK. And we want those for k from 1 to n. So these determinants of the AKs, those are called the leading principal minors. If all of these are strictly positive, so 0 is not sufficient, all of these need to be strictly positive. And second, for the negative definiteness, A is negative definite if the following conditions hold. Again, for the leading principal minors. So this is a little more complicated. It's deceiving to think, well, the determinants have to be negative. That is not the case. So watch out there. What we need is the determinants of the AKs are negative for all odd k. So for k equals 1, 3, 5, and so on, we actually need a negative determinant. But for all the others, we need a positive determinant. And again, it's strictly negative, strictly positive. So determinant of AK is strictly positive for all even k in 1 to n. Okay, so watch out for that. This is the odd case here. And this is the even case. And that is Sylvester's criterion. Let me give you a very quick illustration of these leading principal minors. So if we have this matrix A, looks like this. Then we can start at the upper left corner here with a 1 by 1 matrix. That would be A1, and the determinant of this is the first leading principal minor. Then we'd include the next column and the next row. So this is a 2 by 2 matrix, that would be A2, and so on. So we move on in this way until we get to the full matrix. So once we have all columns and all rows, that's the leading principal minor AN. Okay, and AN is then an n by n matrix. That's the full matrix A. Now let me also give you a quick rationale for that strange criterion for the negative definiteness. You remember that A is negative definite if and only if minus A is positive definite. So A is negative definite if and only if minus A is positive definite. Well, that means by Sylvester's criterion, the determinants of the minus AKs, those all have to be positive for all k. And that means, well, you could take out that minus sign, and remember, for a determinant you have to take out the minus signs by a row. You can take out a constant from a row. We have k rows here, so we get k times this sign minus 1. So this is minus 1 to the k determinant of the AK, and that needs to be positive. And of course that minus 1 to the k, that changes signs with k. So if k is odd, this is negative, then the determinant needs to be negative too. If k is even, minus 1 to the k is positive, then the determinant needs to be positive. Okay, and this leads to the unusual criterion for negative definiteness. So don't be deceived, don't take the easy way here, yeah? That's the wrong way in this case. Okay, so that concludes Sylvester's criterion. Pretty simple if you just compute a few determinants. Let's conclude with a couple of examples to see how this is applied. First, a very easy matrix. Let's say A is the matrix 2, 0, 0, 2. Then, well, obviously, the determinant of A1, that is the determinant of just this first matrix here of 2. Yeah, so that's A1. That is 2 and that is positive, so the matrix could be positive definite. The determinant of A2, that's this whole matrix here. So 2, 0, 0, 2. That's also easy to compute, that's 4, and that's positive again. So A is positive definite. Okay, that was an easy one. Next matrix that is a little more complicated, we'll have a look at the matrix -2, 3, 3, -2. That matrix is obviously symmetric. We should check this before. The first one was diagonal, so that was trivial. Okay, that's a symmetric matrix. And again, let's apply Sylvester's criterion. We'll start with this one here. This is A1. So determinant of A1 is actually determinant of just -2. That's -2. That's less than 0. So it starts with a negative entry. It cannot be positively finite anymore, but it could still be negatively finite. And to check that, we'll have to have a look at the second leading principal minor. This is A2. So we need the determinant of the whole matrix. And that is 4 minus 9, which is -5, so that's negative as well. And remember, Sylvester's criterion said the even entries have to be positive. So that means the matrix is indeed not negatively finite. It is indefinite. And finally, an example of a 3 by 3 matrix here. Let's take this one. 2, -1, -1, -1, 2, 1, and -1, 1, 1. Again, that matrix is symmetric. Please don't forget to check that. And let's go through the determinants. The first one is easy, that A1. That's just 2. So that's positive. It could be a positive definite matrix. It cannot be negative definite anymore. Then we have A2. A2 is 2, -1, -1, 2. So we have 4 minus 1, that's 3. So again, positive. It's good. And one last determinant to check. So that determinant of A3, we still need to check that one. That is the determinant of 2, -1, -1, -1, 2, 1, -1, 1, 1. Okay, let's simplify things a little before we actually compute that. Let's do a Gaussian elimination and say, let's subtract the second row from the third and add the second row twice to the first one to get a few zeros in there. So we just do these Gaussian elimination steps to get the determinant of, let's see, we keep the second row, that's -1, 2, 1. The first row will become 2 minus 2, that's a 0. Then there's a -1 plus 4, that's a 3. And a -1 plus 2, that's a +1. And the last row, we subtract the second row from the last row, so we get a 0 here. That's 1 minus 1, that's a, well, sorry, 1 minus 2, that's a -1 here. And a 1 minus 1, that's a 0 here. And then we do Laplacian expansion with respect to the first column. The only entry in that column is this -1 entry here, so that is a -1. To determine the sign, that's in the second row and the first column, so times -1 to 2 plus 1. And the remaining determinant is then 3, 1, -1, 0. Okay, so what we get is -1 to the fourth, that's a +1. Times, and that determinant here is 0 minus -1, so +1. So that is 1, and that's again positive. And that means this matrix here, A, is a positive definite matrix. So that concludes our examples. for today. Thanks for watching, and I'll see you in one of our next videos.